Welcome everybody to our current Latin American webinar of physics. It is my great honor and pleasure to introduce Dr. Diego Rubiera-Garcia, which is currently a research fellow at the Institute of Astrophysics and Space Sciences at Lisbon University. Diego got his PhD in 2008 from University of Oviedo in Spain. Then he moved to France to Observatory de Paris Moudon. Then he went to Oviedo again, and then to Brazil, to Paraíba Federal University. Then he moved to China at Fudan University, and now is currently, as I said before, at Lisbon University. Today, he will talk about surviving from a journey into a black hole. Diego is an expert in extensions of general relativity, metric-affine spaces, black hole, non-singular solutions, and what is perhaps called mathematical properties of general relativity. Please remember that you can ask questions over using like Twitter. You can also use write your questions over the YouTube channel, and then at the end of the transmission, we will tell your questions to Diego so that he can answer all your questions. Okay, so Diego, let me. It's all yours.
Hear me?
Yes. Okay, so now you can share your screen. We can start.
Okay, so I share the window. Okay. Can you see it?
Yeah, perfect.
Okay. Okay, so shall I start?
Yep.
Yes,
Perfect. Yes. Go ahead.
Okay. So first of all, thanks to Alejandro for inviting me to this new way of giving a seminar. So it's my first experience with these webinars. So it's a great idea to share this research material with people around the world. So today, I choose this fancy title because I think it captures quite well what is the intent of this research that I've been doing in the last maybe 4 or 5 years. So actually, this is a small part of a larger piece of research, my investigation, which is extending general relativity because of different motivations. So we have been using black holes as a way of testing mathematical, physical, phenomenological deviation with respect to general relativity. So this talk I'm going to focus on a very particular aspect of these black holes, which is essentially trying to ask the question of what will happen to a physical observer that crosses the event horizon of a black hole. So what will be the fate of this observer? When you ask this question to general relativity, so you find an answer that makes little sense. So I'm trying to explain why this makes little sense and why this motivates to general relativity to address black holes. Then I have tried to keep the technical issues to a minimum. Some passages of the talk cannot be helped, so you will see some involved equations. So I will try to explain this in quite simple terms, but so I hope that the level is reasonable enough for most of the people to follow. Okay, so by now we have plenty of evidence supporting that the black holes are real objects in the universe. So the latest piece of evidence that we got was the verification of the existence of gravitational waves 100 years after their formulation within general relativity. So the first event, black hole detection, was in 2015. So it was explained, so it was compatible with general relativity expectations for the merger of two black holes. So basically, what many groups around the world are doing about these gravitational waves is, so they run numerically the Einstein equations using different kinds of black holes. So most notably, this merger depends on of the masses and spins of the black holes, and then they produce a characteristic signal. This is what we can see here in these plots. So here, the reconstruction of the signal, we see very clearly the three characteristic phases of a black hole merger, which is the approximation phases, because it is fully compatible with the expectation. At the same time, 2 years later, in these two events, so this refers to the gravitational wave detection, it refers to the electromagnetic wave detection. So this event, instead of two black holes, the merger of two black hole solutions, is associated to the merger of two neutron stars. So this offers new windows, not only on the to try to explain important phenomenology regarding neutron stars, such as the equation of state inside neutron stars, but it also offers a very interesting playground for testing deviations from general relativity in the strong field regime. So this is very relevant for modified theories of gravity that propose that general relativity is not the ultimate theory of gravitational interaction. Many of these theories have been proposed using cosmological considerations, in the sense that they are constructed as alternatives to the lambda CDM model, the standard cosmological model. So the results reported by Lisa Virgo and satellite collaborations about the observation of gravitational waves and the associated electromagnetic radiation have offered important insights on these modified theories of gravity, or better said, on the compatibility of these theories of modified gravity with gravitational wave observations. And particularly, the fact that the gravitational waves and the electromagnetic waves were received here on Earth with a few seconds difference tells you that they travel these two waves travel in vacuum approximately at the same speed, because given the far distance from these objects, should any difference on propagation of these waves exist, this will have been manifested by different arrival times of these two waves here on Earth. So the fact that we approximately receive them at the same time has translated into experimental constraint of one part into 10 to the 16 parts. But this is such a strong constraint that indeed has allowed us to rule out a large number of cosmological models. So a few days after this discovery of this gravitational wave for neutron stars, so there were many papers on arXiv making an examination of different theories of gravity to see whether they are compatible with this observation or not. I particularly call your attention to this nice paper by Tiago Malacari, where they have some tables where they explain very nicely what cosmologically viable theories, they still are viable from the point of view of gravitational wave observations, and those that are no longer viable. At the same time, there are other observations from gravitational waves, like the fact that another paper released by LIGO, they found that you can only find purely tensor polarizations. Indeed, general relativity predicts that in vacuum, the only 2 degrees of freedom, the two polarizations of the gravitational field, are propagated. But there are many modifications of general relativity that predict the existence of other polarizations. These polarizations have not been found, and actually purely scalar vector polarization has been, according to this result, ruled out by these observations. So other polarizations, or the mixture of polarization between tensor, scalar, and vector will be tested in the future experiments. So this will allow to put additional constraints upon these modifications of general relativity. But there is a need of search for new models in order to understand their theoretical and phenomenological consequences. In this sense, a good guiding principle is given, perhaps, the Schwarzschild platform. So during the case, there have been a number of mathematical developments that have been now formulated as theorems or singularities. And these theorems tells you that if general relativity is the ultimate theory of classical gravitation, then the emergence of space-time singularities are unavoidable within this theory. The simplest example, as I said, is Schwarzschild solution. So This is just the solution representing the gravitational field outside of a spherical symmetric body, mass m here, right? So actually, it took 40, 50 years to fully understand what this solution has to hide. And actually, it has been found that there are two regions, 1 and 2, within the solution. So basically, region 1 is the solution external to the event horizon, but in appropriate coordinates, you can extend this solution beyond the event horizon up to the center of the solution. So this is nowadays understood as the classical structure of a black hole solution. The problem with this is that this solution is not fully satisfactory. If you want to know exactly what happens at the center of the solution, you find a number of problems related to the fact that the Schwarzschild solution is a vacuum solution of space-time, which is, and the field equations of this solution are not solved at the center of the star, at the center of the solution, sorry. Indeed, if you try to associate a point particle at the center of the solution as generating a gravitational field of this object, this cannot be. The Einstein equations with this source are not consistent. If you insist on trying to build this, building a model of gravitational collapse, you find that the matter that falls into the innermost part of region 1 or region 2, the energy density of the matter field there will grow without bound as the collapse goes on. If you try to measure also the curvature of space-time, you will find that this curvature also diverges. So at the end of the day, you get at the center of this object, you get divergences, infinities, singularities. So there is something strange happening at the center of the black hole. So despite the observational success of general relativity, there is at the theoretical level a fundamental problem related to the lack of predictability and determinism when you try to understand what's happening in the innermost region of a black hole. Actually, it's difficult to explain what a space singularity is, because this is something fundamentally different from another kind of singularities we are used to in physics. Because as opposed to other kinds of singularities, such as the divergence of Coulomb field in classical electrodynamics, these singularities do not correspond to some divergence of fields occurring upon a fixed space-time. Actually, these singularities are occurring on the structure of space-time itself. So because of this, it's difficult to capture the intuitive notion of what a singularity is, and the theory of singularities offer little clue about this. They tell you that singularity will occur, information about what a singularity actually is. So it's natural to think that since in general relativity, gravity is a matter of the curvature of the space-time, so if something is going is wrong, has to be related to something going in with the curvature of the space-time. So in this sense, one will be tempted to study these places where curvature scalars could blow up. So we are dealing with the scalars in order to avoid artificial singularities that could be avoided just by a change of basis. But there are several problems with the blow up with this characterization of singularities in terms of blow up curvature scalars. If you have a look at Wall's book in General Relativity, this is explained very nicely why studying the blow up of curvature is unsatisfactory, because this doesn't exhaust all the possible kinds of pathological behavior. But to me, the most important point is that the most reliable results that we have about these singularities lie on the singularity theorems, and in these theorems there is no reference to the blow up of curvature scalars. Actually, these theorems make use of a different concept, which is something which is called geodesic completeness. This concept is important because finite geodesics are associated to the free fall of physical observers, while null geodesic is associated to the propagation of light rays and transmission of information. So undermining the geodesic completeness in your physical theory means that you impose the physical principle that in your theories of nature there exists no the possibility of creation of something from nothing, or disappearance of information into nothingness. So imposing the principle of geodesic completeness means that if a space-time is geodesically incomplete, then it's singular. But the other way around is not true. So in the case of Schwarzschild and Dresden-Nostrom solutions of general relativity, it's very clear to see why they are singular. They are geodesically incomplete. So they contain at least one incomplete geodesic. So in this theory, information can be created out of nothing or disappear into nothing. So this cannot be. This is clearly a reasonable principle. And the power of the singularity theorem lies on the fact that they implied that in general relativity, these singularities occur under very general assumptions on the structure of space-time and the behavior of the matter fields. And in particular, does not depend on particular symmetries that you have assumed in order to build your solution. Despite this lore, still, most of the community still insists on using the characterization of bounded scalars to build what they call regular black holes. So this idea of bounding the curvature scalars have produced a lot of approaches. So, I have only underlined here a few. So like thin wormholes, blank scale effects in order to counterbalance gravitational collapse, etc. Even more fundamental approaches such as string theory or low quantum gravity. In any case, in our research, we accept this need of going beyond general relativity in order to try to address the problem with space-time singularities. So our approach, in this sense, is more modest than fundamental approaches. We still accept that gravitation is a matter of is related to the curvature of the space-time. So we build up our theories with objects that are whose basic blocks are the metric and the connection. So for the connection, you build the Riemann tensor and make a contraction of the Riemann tensor either with the metric or with itself. You build different objects in order to construct your theory of gravity. So in the simplest case, where you build your Lagrangian as simply the scalar curvature, so this is the contraction of the metric with the Ricci tensor. So this is general relativity. But there are much more possibilities here. Then you have several options here, because you have two independent fields here, you have the metric and the connection. You can impose that the connection is compatible with the metric. Otherwise, it satisfies this equation, which means that your connection will be given by the Christoffel symbols of the metric. This is exactly the situation that you have in general relativity. And this approach to build these theories is called the metric approach. There is a problem with this approach when you go beyond general relativity. So if you build the field equation for this action by the standard procedure of the standard variational procedure, so make a variation with respect to the metric, so you get this set of equations here. You have the standard numerator tensor on the right hand side, and you have new objects here. The problem with this, because of this covariant derivative and this derivative that appear here, so in general, this set of equations is of fourth order. In general relativity, we have second order field equations. Here we have fourth order equations. And because of the presence of this term, you immediately run into troubles when you formulate your theory into this. Because of these fourth order equations, you usually have cause-like instabilities. You have a potential incompatibility of these theories with solar system experiments. There are some exceptions, like Lovelock theories of gravity. Even in F of R theories of gravity, you have higher fourth order equations, but there are no cause. But there is a way you can do things better than this metric approach. If you still keep to the idea that metric and connection are independent objects, so what you have to do here in what is called the metric-affine approach is to make a variation of this action with respect to the metric and with respect to the connection independently. So you make this variation, you have the variation with respect to the metric and the variation with respect to the connection. And because these two objects are independent, so you have two independent sets of equations. At first sight, it doesn't look like a very big deal, because instead of having one set of equations, then you have two sets of equations. But playing wise with these equations, they can be recast into this form. So what you have in this form is, on the left-hand side, you have the Einstein tensor of some metric, which we call here the auxiliary metric. But this auxiliary metric is related to the space-time metric in this way. So there is some matricial object, 4 times 4 object here. You are in 4 space-time dimensions. And the trick, the important point about these theories is that this object here depends on cell only on the energy momentum tensor that appears here. And because this object appears here and also inside the gravitational Lagrangian, everything that you have here on the right-hand side of the field equations is a function of the energy momentum tensor. These equations are just Einstein equations with a modified energy momentum tensor on the right-hand side. So it mimics the philosophy of general relativity. And because, again, this metric here is related to the space-time metric, via a matrix that depends on the matter field. So once you solve this Einstein-like equation, you go back to the space-time metric using these algebraic transformations, and then you find the final solution for your problem. But these equations are manifestly second order. And because in vacuum, they give you exactly general relativity, so there are no ghosts, there is automatically compatibility with solar system experiments and also with gravitational wave observation made so far. And also, if you, in these equations, you put your gravity Lagrangian to be the one of the Einstein field Lagrangian, then you get that your field equations, for this case, are also general relativity. So this metric-affine formulation is completely compatible with general relativity when you choose the Einstein field Lagrangian. But if you go beyond general relativity, you get these Einstein-like equations, and then you have a new playground to play with these theories. So there are many scenarios that you can play with, and because in this talk we are interested in black holes, so we are going to deal first with spherically symmetric solutions. So any static spherically symmetric solution, without loss of generality, can be written this way with two independent functions that specify fully the geometry. So in some coordinates, you can always write a line element this way. So the ER examples for spherically symmetric solutions are the one of Schwarzschild and the one of Lisbon, where the radial function trivializes, and you have this for the other metric function. These solutions correspond to black holes if this function has at least 1 0. For Schwarzschild, this is always the case. For Lisbon, depends on whether this mass and charge satisfy so constraint. So you can do the same in this metric-affine theories of gravity that I just described and try to look for spherical symmetric solutions. So if you consider a quadratic Lagrangian like this one, so you have the Ricci scalar square, you have the Ricci scalar here, and the Ricci scalar and the Ricci square, right? You can also include the contraction of the Riemann tensor with itself, but because of the Gauss topological invariant, can always be removed in favor of these other two invariants just by recasting these two constants to other values. So using these equations that I mentioned before and using the relation, so you for this theory of gravity, metric-affine theory of gravity, you can solve these equations. And you get that these functions of the Schwarzschild transform into this form. There are two differences. First, this metric function, so it's a little bit more involved than this here. Essentially, this function will tell you when horizons are present. In this theories, depending on mass, charge, and the value of this parameter, you will have different numbers of horizons. It's even more important the behavior of the radial function. As I said, in the case of general relativity, radial function trivializes, but here it doesn't. They have something new, these two objects, so there is some new radial coordinate, which is the scale, in order to deal with dimensionless coordinates. So in this, let's say, core radius here, depends on the charge, depends on this new scale that I have introduced here, depends on the mass, whatever. And if you study the standard of the solutions, you find that for large distances, you recover the Dresden-Boston solution. But if you are near the innermost region of the solution, it turns out that for a finite value of the radial function, the metric function takes this form, so you have some constants here, and then you have 1 over r behavior here. So this is clearly different from the behavior that we got in the case of Dresden-Boston solution. So the innermost region of this solution are completely different from the Dresden-Boston one. And indeed, if you analyze the behavior of the radial function, what you get is this kind of structure. So this function here is depicted here in dimensionless form. And what you see here is that here everything looks like general relativity, because of consistency with this with the reduction of this method to Dresden-Boston. And when you get near the center, so the radial function gets to a minimum and then bounces off. Actually, this is absolutely compatible with the expected behavior of wormholes. So wormhole is a kind of solution that also exists in general relativity, but in order to build it in general relativity, you have to violate energy conditions. Because of this, these solutions are regarded unphysical. But in the case of metric-affine quadratic model I just presented, this is not so, because we're just considering a magnetic Maxwell field satisfy energy conditions. So this is satisfying all the physical principles in this sense. But there could be troubles here, the minimum value of the function where the wormhole throw is located, because in general, curvature divergences will arise. So it's a reasonable question to ask whether the presence of these curvature divergences at the wormhole throw will not imply that the solutions are singular. So then we go to the full arsenal that we already know in general relativity about how we can test the regularity of a solution. The first tool in this arsenal is to go to geodesic behavior. So the geodesic equation can always be cast this way. In metric-affine theories, there is a potential interpretation problem because you have the components of the connection here. But we have, in principle, two different connections. There is the connection associated to the metric, which defines the Christoffel symbols and a natural set of geodesics. There is also so-called geodesic associated independent connection. So which one you should choose here? If you assume the Einstein equivalence principle and the fact that matter is not coupled directly with independent connection, which is what happens in our setting, then the physical geodesics will be towards the metric. If you use the other connection, what will happen is that you can always recast this equation, this being the standard Levi-Civita connection, but there will be new terms here that will appear as an extra form. This is not so if you have only couple the matter to the metric and not to the connection like you do in general relativity. So because we are in a spherical space-time, there are two constant quantities, which is the angular momentum and the total energy. And you can always rewrite this geodesic equation in terms of geodesic tangent vector, like this way. So this equation is exactly what you get in general relativity, except here there is a new factor. This function is not the one that you have in general relativity, but this is the wormhole radial constant. This constant appears here. For 0 corresponds to null geodesic, let's say photons. And for 1, it corresponds to physical observers. So in order to see whether these solutions are geodesically complete or not, we integrate this equation. When you integrate this equation in the simplest case, which is radial null geodesic, so this is just photons heading directly into the wormhole throw, this means an analytical integration when you deplete it. So you go here for asymptotic infinity, you close the wormhole throw. In general relativity, you will get to 0. Geodesic stops there, but here, because of the wormhole, you can close without any problem. So this affine parameter is geodesically complete for any value of mass and charge. In general relativity, as I said, the affine parameter stops here. There is no possibility of extending there. So these solutions are geodesically incomplete. In general relativity, this is why it said that the Reisner-Nostrom solution in general relativity is singular. Here, it's not singular in the sense of geodesic completeness. If you also make the same analysis here for non-radial and also for time-like geodesics, you would, here you can, this paper, you will find that all these geodesics are complete. So all these solutions are geodesically complete for all values of mass and for all values of charge. Okay, so test pass, but there are more tests that you can apply. Another test is what is the physical implication of curvature divergences? Because curvature divergences in these solutions at the wormhole throw might go very large, this might potentially induce very large tidal forces that rip any physical body apart in a effect which is called the spaghettization effect. So this is due to different forces between the feet and the head of a potential astronaut falling into a black hole. At the same time, these tidal forces will also stretch this observer in the angular direction. So at the end, you have a spaghetti because it's launched this way and stretched this way. Actually, this intuitive idea can be put in mathematical in rigorous mathematical terms by modeling observer in terms of a congruence, which is nothing but to assume that each particle of the body is free falling upon its own geodesics. But because of the existence of tidal forces, each geodesic can feel a force that can hit the body apart. So you can find three Jacobi vectors that tells you which is the relation between each particle of the body. The choosing of these vectors is arbitrary, but you can define a volume that is not arbitrary. So the volume is basically the determinant of the three Jacobi vectors that you have chosen along the congruence. And there are several criteria, the Behaviour literature, that tell you, according to these guys and others, that if when you approach the problematic region where curvature goes very high, if this volume goes to 0, then you have what is called a strong type or a crashing type singularity. So this is interpreted, as I said, as tidal forces tearing the observer apart in the radial direction, right? So this will imply that causal contact is lost between different parts and the observer is strong. So even if individual pointless without size points of the geodesics can cross through the wormhole, it potentially means that standard observers will get apart and they do not survive to the transit through the wormhole. When you apply the same criterion, build these vectors and this volume in these modified black holes that I just saw, you get this result, that the volume, instead of going to zero, goes to infinity. And this result has not a proper interpretation within this criterion. So you need to do something in order to see what are the physical consequences of this. So in this very technical detail paper, what we did intuitively was to model again these objects, physical observer using a congruence, and then send line rays between two parts of the body on a round trip, allow when a body is crossing the problematic region with curvature divergences, and see if this round trip between these two parts of the body is causal or not, whether it can be effectively done before below the speed of light or not. And what we find is that using comoving coordinate, this is exactly what happens. Each part of the physical observer near the wormhole is in causal contact with any other part. So this means that physical interactions staying in the body might be effectively transmitted and are not unavoidably destroyed upon the transit. A third criterion is that instead of using individual geodesics or physical body made of geodesics, use waves. So make tests with waves with the wormhole. So, for example, you can take a scalar wave equation, so you decompose it into the standard modes or the radial, angular, and temporal modes. Make approximations near the wormhole throw to deal with analytical solutions, and then you can compute at any scattering experiment transmission and reflection factors. And when you do this, is that you can compute these factors, transmission and reflection factors, no problem. Everything seems to be well posed. Part of the signal process through the wormhole, part of the signal is reflected. And curvature divergences are not affecting this wave propagation, they are affecting geodesic completeness. So this is another test that these solutions pass. The fourth test that we try is that, geodesics are complete. But because of due to the principle of general covariance that tells you that observers with any arbitrary motion are physically equivalent to any other one. So any observer with any arbitrary motion should also have a complete path. Otherwise, it could happen the situation where all geodesics, in the sense that all free-falling physical observers have complete paths, but if you are in a spacecraft and you switch on or your engines with some acceleration or deceleration, you could find an incomplete path. In order to avoid these pathological situations, you need to describe the motion of accelerated observers, static, spherical, symmetric spacetime with some acceleration. It's assumed to be finite. And then you get that the standard geodesic equation, which are these two terms and this energy, it gets modified by another term that depends on the linear acceleration here. You can apply this completely general formula to the models I was mentioning before. Then you pick up some new term here. This integral appears here, gets a specific explicit form, which is this one. And then again, you do the same. You explore all the spectra of mass and charge and acceleration present in your model. And what you find, this paper, is that all the paths of all accelerated observers with finite acceleration, no matter the value of the acceleration, the mass and charge, can be indefinitely extended. So all the paths of accelerated observers in these solutions are complete. Because we are running out of time, so I just go to the conclusions of this. So the question is, my spacecraft provide a journey into one of these modified black holes, replacing the rest of the solution of general relativity. So we have done this. First, we realized that after crossing the event horizon, both photons and stable observers might get to the wormhole through infinite proper time. And then we used 4 different criteria: geodesic completeness, so all trajectories, so like annual geodesics are complete. The tidal forces do not necessarily destroy physical observers because the parts of the body are at all times in causal contact. The scattering of waves of the wormhole is well posed. You can compute transmission and circumflexion, no problem. And the paths of accelerated observers, no matter the value of the finite local acceleration, they are always complete. Because of this, these solutions are non-singular according to this criteria. So there is no need of evoking any cosmic censorship conjecture in order to rule out the possibility of the existence of solutions without horizons, because in these cases there are no naked singularity to hide. So this opens the door to the possibility of existence of ultra-compact naked objects. But of course, we have been studying the problem of static spherically symmetric black holes. This is obviously an oversimplified scenario because real black holes in the universe do rotate. So in order to see whether this picture of the black hole and this picture of the non-singularity of them, of these black holes, is real or not, from a theoretical point of view, we need to obtain the analog solution with rotation, and then again make all these things, all these tests. This is something we are doing, is work in progress. This is a very difficult problem in order to obtain an analytical solution for this same setup with rotation. We are working on it, making large progresses, so maybe before the end of this year, this will be ready. So the final message of this talk is that geometrical approaches beyond general relativity, maintaining the same core principles that you have in general relativity, say equivalence principle, gravitational manifestation of a curious space-time. So we maintain the same principles, just stay in the action, rethink the role of the physical object that you have in your theory. And when you apply this to objects like black holes or the very early universe, you find the result that you can avoid space-time singularities in both the scenarios, both in early cosmology and in say black holes. These theories have also other particularly interesting properties from the point of view of astrophysics cosmology. So this work deals with some of these models. The final message of this talk is that there is a great importance of the use of multidimensional astronomy in the years to come in order to discriminate between different theories of gravity that are able to be, whose compact objects will be able to be compatible with the observation of gravitational waves, just with different masses and spins of the corresponding objects. So it's necessary to gather both the theoretical knowledge that can come from many stations of gravity, particularly those that have underlined here, and those observations that we can make with compact objects from using gravitational astronomy. So that's everything. Thank you very much for your attention. For any questions, I will be happy to answer.
Thank you, Diego, for this nice talk. Let me see if we have something in the YouTube channel. I believe we have one question from Shadusha. Sorry if I did not pronounce that. Diego, you can go and see, if you want, you can see in the YouTube, yes, the Google Hangout. I shared the question, so maybe you want to read it.
Okay, so dark energy cosmology, which is the oldest black hole discovered by humans, many farthest probably the big flow that matter around galaxy cluster by which reside light behind it. Well, I actually don't understand very well the question.
Yeah, it seems it's asking like if by chance you know which is the oldest black hole we have seen.
Well, I'm not very aware of the details about which is it, but probably he's talking about gravitational lensing around a black hole, depicted from dark matter galaxy by which reside behind it. I don't know if he's asking about this thing, because actually a way of testing deviation from general relativity, precisely using black holes. When black holes can capture photons, these photons that travel around the black hole, particularly around the innermost circular orbit, they can tour around the black hole several times before being released and going back to arriving to some observer. And it turns out that the optical properties of these photons reveal the physical features of the black hole that have captured them. Okay, so particularly in the case of general relativity, mass and speed. In the case of black holes in modified theories of gravity, also the underlying producing this object. It's a way of testing the viability of the solutions.
Okay, thank you. If you want, you can stop sharing the screen so we can see you.
Okay. Okay.
Well, I do have a question, which is, could you please comment a little bit on the stability of those wormholes when you?
Oh, that's yeah. Actually, studying the stability of black holes is a very tricky point. So what we did was to study stability against tensorial perturbations. Actually, there is a problem in the, well, not a problem, a particular feature of these theories. So I said that there are two sets of metrics. There is the space-time metric, and there is another metric that I call auxiliary metric, Q. So it turns out that for this for black holes, for propagation of waves, so it's the space-time metric, is the physical object, but it has been already shown in many papers that the auxiliary metric actually is the one that gravitational waves see, right? So when you study stability against tensorial perturbation of these solutions, so you have to study the behavior of these waves on this auxiliary metric. And then there becomes a problem because it has been shown that some of these solutions with black holes and with the early universe, there can be instabilities, in the sense that there can be growing modes that gets amplified. So even if your solution is okay, static, as soon as you consider gravitational wave into the picture, quickly it gets destroyed, right? So this is a first test, important test for the stability of both black hole solutions and cosmological solutions. Right? Passing by, this is compatible, despite gravitational waves propagate on a different metric, this is compatible with gravitational wave observations because the difference between these two metrics happens in environments of high energy density. But the observations regarding the quality of the propagation of the speed of light and the speed of gravitational wave refer to propagation in vacuum. And in vacuum, these two metrics are invited. It is the matter fields, so in vacuum, this matrix is identity, these two metrics coincide. So they are compatible with gravitational wave observation because of this, but the potential instability with respect to this auxiliary metric might threaten the theoretical viability.
Okay, thank you. So yeah, it was nice in your talk because some people think, I believe, that modifying general relativity is like you just have a huge bag and then you start pulling theories and then you just make calculation. But in fact, it's very hard, like, because especially what you mentioned during your talk, which is it must first pass all the plethora of experiments and tests that we know. So it's very hard, like proposing modifications, and I really like it.
Actually, when you think on this, so there are many theories that are past experimental the solar system experiments, and then many of these models, as I said in the introduction, they are proposed as viable alternatives to the standard cosmological model, in the sense that might be statistically as significant as the lambda CDM model. So what's funny about this multi-dimensional astronomy is that a single observation, the propagation of gravitational waves, it has been able to roll out many theories of gravity that are perfectly fine from the point of view of cosmology, but they are not fine from the point of astrophysics, right? So my hope is that in the near future, as we are accumulating more and more hundreds, in the future thousands of observational gravitational waves from combat objects, we will be able to put to experimental direct observational tests many of these theories that are built in such a way that are consistent with cosmology.
Okay, thank you. Do we have any other question from the low physics coordinators?
Yeah, I have one question for Diego. Diego, first of all, it's very interesting the talk on all the effort that are around in the area to see this difference between general relativity and the modification. So I have a couple of questions in the sense because many in these theories of when they study black holes, also sometimes they include also the case when the black hole is charged. Is this also because well, it's been in black holes, but you mentioned at the end in your conclusion that is your work in progress. But if you have any comments about what happened when in this context the black hole get a charge?
Yeah, actually, the solution, the split solution I was presenting is exactly the charge solution. And the reason because of this is because if you consider the counterpart of the vacuum Schwarzschild solution, this is exactly the same solution as in general relativity. And the reason is because the new corrections that appear on this theory to general relativity solution are mediated by the matter fields. If there are no matter fields, and Schwarzschild are vacuum solutions, so the solution is the same as that in general relativity. So the Schwarzschild solution in this theory is the Schwarzschild solution in general relativity. So we have included the charts in order to obtain deviation with respect to general relativity solution, in this case, the Reis-Nelson solution. Now, for the relativity solution, because of the same reason as the Schwarzschild one, the Kerr solution of these theories is exactly the same as the one of general relativity. So, in order to obtain deviations, you need to consider the Kerr-Newman solution. Now, it's very well known that for astrophysical purposes, the charge is completely negligible because the spin and the mass dominates overwhelmingly the contribution of the charge, right? But from the theoretical point of view, these black holes are never completely discharged because of many different reasons. So they always retain a tiny amount of charge that can be negligible for astrophysical processes, but it's not negligible at all from the point of view of the physical structure and the mathematical properties of this black hole, potentially the phenomenological properties. Indeed, we have verified that even a very tiny amount of charge is able to produce, will be able to produce large changes in the structure of the solution. So because of this, we are very motivated to find the counterpart of the Kerr-Newman solution, which, as I said, is a very daunting task, difficult to do. But we recently, this year, we released a paper because the structure of this equation resembles so much that of general relativity with the Einstein tensor on the left-hand side, all the matter fields on the right-hand side, that it's tempting to compare the equation with general relativity and to find a potential correspondence between solution of general relativity, solution of this theory. This is exactly what we found in this theory. We found a kind of map. I didn't mention it in the talk because there was not enough time. But there is a map that tells you how to map a known solution of general relativity to that of one of these theories using purely algebraic transformations instead of solving differential equations, which is the biggest challenge when you try to find solution on this. This is very important because when you try to do gravitational wave astronomy using black holes, there are many groups around the world with very well developed mathematical and particularly computational methods that are very strongly tied to the particular structure of the Einstein field equations. And these methods are very difficult to translate to the case of these theories. Not because of this, the existence of this map, that way is not needed. What you need is just to find a particular scenario in the case of one of these metric-affine theories, let's say the Kerr-Newman solution. When you find the correspondence with the general relativity solution, then you have to solve the Einstein equation into this. You find the corresponding solution of general relativity using this map, and then map it into the one of metric-affine theory. In this way, you can use the full power of the computational methods developed in the context of GR and apply it directly to this theory.
Okay.
Sorry.
I have a second one.
Yeah.
The second question. No, yeah. Thank you for the answers. But yeah, and the second question was related with in this kind of modified theories. Is there a better chance, for instance, to study effects related with quantum gravity, or to put together particle physics in this metric background kind of? The stuff that usually is harder to do in general relativity because the theory explodes from the point of view of quantum mechanics. Or is there also approaches to try to make it smooth, the transition between quantum and gravity in the sense?
Yeah, well, I didn't mention anything about quantum gravity motivations because
first, I know. It's just if you have some comments about that, because
well, yeah, we're using a classical approach in the sense that we are including all these new invariants into the action. This classical invariant motivated by the quantum theory, by the theory in quantum fields, pure space-time, that tells you that general relativity has to be supplemented by additional cumulative terms. And we just kept ourselves at the quadratic level of the field equations. We didn't go further. We didn't even claim about where the scale present into this theory comes from. So this L epsilon that appear on the theory could be Planck's scale or could be something completely different. Actually, we are more inclined to see something completely different because our approach, instead of using quantum gravity, we try to rethink the basic principles that build general relativity. In the same, what is the physical role played by different mathematical structures? So I mentioned about the connection, the metric, the sense that they are independent. Actually, they are independent in general relativity too. It's just that because of the structure of the Einstein-Rubiera-Garcia, the metric formulation is completely equivalent, right? But because of the way that historically general relativity has been taught, usually people assume that metric approach is the only approach, and then just supplement the action with new terms, but assuming that the connection is the Levy-Chirp. But if you recognize the physical role of these new quantities, so you have the independent metric connection, so you will up with these things. And there are even more degrees of freedom in the sense that the connection, we usually, I didn't mention it explicitly, we are assuming that the connection is symmetric. Actually, the connection has a non-symmetric part, which is torsion, the symmetric part. Torsion is usually neglected on the field equations because as long as you don't couple spins, so plays no role. But actually, both torsion and the fact that the connection is not metric compatible, that introduces another object which is not metricity. Metricity contains new scales associated to them that are not Planck scales, and they are much below the energies that are expected to Planck scale to occur, right? So the fact that there are important geometrical elements that have been leaving aside when trying to study general relativity, maybe you are overlooking something, some key results, so some key elements that are needed in order to understand how general relativity could be extended without entering into the realm of of quantum gravity, where we have no much clues about what will happen there. I don't know if I didn't shoot correctly until the point you were mentioning, but
no, yeah, it's very, it was very clear.
Okay, thank you, Diego, and thank you everyone for watching this webinar. Remember that this happens more or less every 2 weeks, and that now we have also introduced a colloquium. I think that's the name we choose, right, Roberto? So that's you can also see all this information in our webpage or the YouTube channel. So thank you, Diego. Thank you, everybody, and stay tuned for more webinars.
Thank you very much for the invitation, Alejandro.
Okay, bye-bye.